So we'll move on to the first module, and before we do that, just a quick recap of what we did in the introduction section. So I showed you a couple of examples of different types of reactions, whether it's combustion reaction, whether it is reforming, gas phase, surface catalytic reactions, and so on, and also showed you the cases where we have the traditional type of reactions where single reaction, two reactions, and so on you're already familiar with, but non-traditional reactions, or what is called as microkinetic mechanisms or detailed mechanisms, where each reaction that is written in the form of an elementary reaction. Okay, so that's the word that we are going to introduce very soon. I have not yet introduced it. The other thing that we did is we spoke about an analogy between a continuous reactor and basically putting your batch reactor on some kind of a conveyor belt, and that's analogy with continuous manufacturing. And over there what we said is this is the equation that we are familiar with for first order reactions in a batch reactor. This is something that we have done in schools as well. Okay, and we replace this T with a residence time tau. Residence time is nothing but Z by U, where Z is the location, U is the velocity. Okay, and if U were constant, you can take U outside, and this is the equation, and this represents the equation of a plug flow reactor. Okay, so all of this we meant primarily as introduction. We will go over these concepts, which will be recap of your undergraduate concepts in probably the next 4 to 5 lectures and one tutorial. This particular part is kinetic rate expression. Okay, and we also call it in terms of source term when it comes to, say, transport type of analysis. Okay, we are going to use the terms replaceably, in the sense, let's say we have a gas phase reactant, okay, that only dissolves in a liquid phase. Okay, from the perspective of gas phase, it's the gas cannot see whether or not there's a reaction taking place in liquid or there's just a dissolution taking place in liquid. Okay, so this idea of source term makes it a little bit more broader. Okay, again, I'm throwing the terms out there. We will go over these terms again and again over the next 12 to 13 weeks. So I'm just introducing some of the terms that we are going to talk about. Okay, this, and we will do this in a bit more detail soon, this will be called as convective term. Okay, and that I will relate it to the transport equations later. Okay, so this is basically what we are going to do over the next couple of lectures. Okay, first take up the CRE type of equations, batch reactor, plug flow reactor, where the derivation of those reactions, those expressions came from your undergraduate work. Okay, then we will talk about how that relates to the transport phenomena type of stuff that you did in your undergrad. Okay, then we will cover mathematical concepts, simple concepts in math, and then we will go on to introduce our fundamental design equations and so on. Okay, so this is the overall, you can call it fundamentals of or preliminaries of reaction engineering, or you can call it recap of undergraduate terms and so on. Okay, we'll start off with definitions, and then we will move on to the key concepts in CRE. Okay, Okay. Okay. So these are the reactors that you have dealt with in your undergraduate. Okay. What are the characteristics of a batch or a semi-batch reactor? Anyone? What are the assumptions and so on behind a batch or a semi-batch reactor?
Unsteady state.
Unsteady.
Step change.
Step change. Step change in what? Okay, fine. I'll just put it in brackets because we will do the analysis without step change, but yeah, we'll talk about that as well.
Same residence time.
Same residence time. Within the entire reactor. What else? Unsteady basically means things change with time. Okay, basically you have a reactor, let's say a liquid phase, it could even be a gas phase reactor. You start at time t equal to 0 and track the progress of the reaction over time. Okay, and that's why it's unsteady. What is meant by same residence time? It's well mixed. That means any location in the reactor is the same as any other location in the reactor. So things only change with time. Things do not change with space. Okay, and that's why it's an ideal reactor. Okay, what are the features of a CSTR? A continuous stirred tank reactor.
Steady state.
Steady state. Sorry?
Progressive.
Progressive change. And that progressive change will be with respect to tau, which is the residence time. What else?
Like a lump system.
Lump system. What else? What do you mean by lumped system? Someone else, of course. What would you understand by lumped system? Or any other terms that are associated. You can use math also if you want.
No spatial variation.
No spatial variation. Both of them we can use. Say, just like a batch reactor, a CSTR is also well mixed. Okay, then what is the difference between a CSTR and a batch reactor?
Continuous in, continuous out.
Continuous in, continuous out. So if you have the same reactor, okay, you have streams that are continuously coming in, streams that are continuously going out. And streams can be plural. You can have multiple streams. Okay, what else? Yeah, in batch reactor, every batch could potentially have different products. In a batch reactor, things do change with time, so it is based on how you charge the batch reactor, and the progress in a batch reactor can vary from batch to batch. Whereas in a CSTR, so a lot of times CSTRs will be started, let's say if they are started now, they will run on for months and months before you need to take a shutdown. Okay, so CSTR want to run them in a very continuous manner for extended periods of time. Okay, now a few terminologies let me introduce. The inlet In the CSTR, I will call that as C in, concentration in. Outlet, we will call this as C out, okay, and the concentration within the reactor, we will call it as C. How is C and C out related? They are equal, okay. So there is one more assumption in a CSTR, is that C out equal to C, okay, which means whatever is coming in the CSTR, that undergoes transformation because it gets well mixed. It loses its identity immediately, okay, because it gets immediately well mixed. What comes out is at the concentration and temperature that is there within the reactor, okay. On the other hand, in a batch reactor, you will start with certain concentration C0, okay, and with time this will change to CT, okay. One of the problems that I find with a lot of first semester PG students is that your undergraduate textbooks use the notation C underscore 0 for both inlet as well as initial. Inlet is different than initial, okay. Initial means what is there at the beginning of your experiment. Inlet is what is coming in the reactor, okay. For example, let us say we are going to do a reaction in a CSTR, and initially that CSTR contains just water. Let's say water is the solvent, okay, and then as the things are coming in, let's say you have let's say an acid and let's say we have this esterification reaction taking place, okay. So let's say you have an acid and an alcohol coming in, and you form an ester, right. So you have acetic acid plus ethanol, they will react to form ethyl acetate, okay. So initially there is no acetic acid, no ethanol within the reactor. It only contains, let's say, some catalyst, but does not contain the reactant A or B. What is coming in is some amount of ethanol, some amount of acetic acid. So the inlet condition is C in, initial condition is C naught, okay. Transient CSTR, if you have done in your undergrad, you would have done right at the end of the course, okay. Otherwise transient CSTR is usually not even done in typical undergraduate, okay. So batch reactor is treated independently, CSTR is treated independently. We are not going to do that. Both batch and CSTRs are well mixed systems. We will assume them in the same umbrella, and then we will take them one as a special case of the more general system, okay. Mostly, yes, with CSTRs we are going to look at steady state analysis. With batch reactor we are going to look at transient analysis, but really, I mean, CSTRs are also transient, truly speaking. That they are just small variations around the steady state, and that's why you need control. So you would have studied in process control, okay. What that is and so on, and how we are going to look at this is what we are going to do over the next 2 days. We will interpret on it. What about the plug flow reactor? Perfectly mixed radially.
Zero mixing axial.
What else? Okay, and then let me remind you the interpretation that we had done. in some future time it will reach from here to here. Okay, so the batch reactor analysis that you do with respect to dc by dt, you will do it with respect to dc by d tau. Okay, so that is analogy number 1. Analogy number 2, now we are free to make that analogy. Let's say we had multiple CSTRs in series, and because it's fluid, we don't necessarily need to move the CSTR physically on the conveyor belt. We can only move the contents of the CSTR on a conveyor belt. Okay, so what I mean by that is you add a pump that does this. Okay, so n CSTRs in series equals TFR. Okay, again we have not yet got into the mathematics of it, which we will get to probably in the second half of this course. We will do a quick recap of the concepts next week, but really, focused attention on batch, continuous and plug flow reactors, designing them, analyzing them and all that. We'll do that in the 7th module, I believe. Okay, so that would be probably 8th or 9th week of this course. Okay, but for now, I hope you got a physical picture in your mind. Okay, and those are the correlations that you want to make. Okay, it sounds very nice and very lucid when you start making this correlations, but essentially what we also need to do is we need to have the math in order to do this analysis. Okay, but again, what we are talking about is, let's say we have a pipe in which fluids are flowing. If you think about a packet of fluid that is perfectly mixed, but it does not interact with the next packets, that means zero axial mixing, that's what a plug flow reactor is. If you meet that requirement, you can treat a plug flow reactor either like large number of CSTRs in series, or like a batch reactor that actually changes its content in space rather than a batch reactor changing its content in time. Okay, and those are the analogies. Now, where do the analogies starts breaking down? Those analogies break down when the simple system meets the real world. Okay, where does it break down? Let's say you have a gas phase reaction with change in number of moles. Okay, so if you have a reactor that is over here and that reaches over here, let's say there were 10 moles here, there were 15 moles over here. Okay, one of the two things are going to happen. Either the volume is same and pressure will be increased by 50%, or pressure will be same, volume will increase by 50%, or something in between the two. Okay, and that's where the rest of the transport equation starts coming in. Okay, and again, undergraduate chemical engineers, you would have studied those epsilon factor, delta factor and all that. That's simply where it comes in from. It comes in not from the analysis of the reactor itself, but changes that happen in flow or volume or pressure because of the reaction that is taking place and the flow that is happening. Okay, so we can, if we break down the problems, we can go and analyze extremely complex systems also, such as explosion, detonation, for example. Detonation is actually used in, for example, during rocket launching. It's a controlled detonation only in one direction. You don't allow it to explode, but you allow it to explode in one direction and the rocket launches. Okay. Usually it's aerospace engineers who look at it, but this is very much in a way a CRE problem. It's very difficult from a regular CRE concepts, because now what is happening is you have a huge amount of pressure built up that releases at very high speed. Okay, and those high speeds, if they reach Mach number of 0.1, 0.2, that process itself affects the overall pressure distribution. That in turn will affect reactions. Okay, but if you break down the concepts, okay, the concept of the source term is what chemists do. Concept of transport equations is what mechanical engineers traditionally do. Combining the two and analyzing them together is what chemical engineers do. Okay, so we would have told you, or your teachers earlier would have told you, is chemistry is not chemical engineering, or chemical engineering not this and that. My proposal to you is to look at chemistry is chemical engineering, mechanical engineering is chemical engineering, any other field of engineering is very much chemical engineering. Okay, and so chemical engineering is all of it and not none of it. So yes, you are going to do chemistry quite a bit in the first 3 weeks. Yes, you are going to do fair bit of transport in the middle 3 weeks, and you are going to combine all of this together in a reaction engineering framework in all the 13 weeks of this course. Okay? Okay, so these were the reactors that we listed yesterday. Okay, any other reactor to add to this? Moving bed reactor. Okay, nice. Okay, is moving bed reactor and the simulated. Okay, moving bed reactor means you take a bed and you move it. Simulated moving bed reactor means on the bed there will be 5 different inlets, 5 different outlets. So inlet, outlet, inlet, outlet, inlet, outlet, inlet, outlet. So you are simulating the moving bed without actually moving the bed. Okay, that's called the simulated moving bed. We probably won't analyze moving bed and simulated moving bed reactors because I haven't worked on it for at least last 20 years. But maybe if I can find an example, maybe we can take it in the very last week of this course. Okay, so can you balance this reaction? Yeah, can probably write it like this, or some of you may have written it okay. So either ways, from a stoichiometric viewpoint, is balanced. Let's just for convenience, let's just work with this guy. Okay, let's say we have 4 species. What is the stoichiometric coefficient for N2? 1. What else? Any other answer? What's the stoichiometric coefficient for N2? Minus 1. How many say 1? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, how many say minus 1? 1, 2, 3, 4, 5, 6. How many say I don't know? How many say 0? I can do this the entire day. All hands must go up. How many say I'm not confident enough to raise my hand? Okay, we'll go again. How many say 1? How many say minus 1? Fully raise your hand. Okay. How many say any other answer? Okay. The convention that we are going to use is reactants are negative, products are positive. So, how many say 1? How many say minus 1 now? Okay, good. We have almost a consensus. Please raise your hands. Okay, don't be shy. It's let's say you're playing cricket. You're 4-year-old. Think you're 4-year-old or 5-year-old, and you're playing cricket for the first time. Okay, unless you go and stand in on the pitch, your coach cannot help you. It's okay if you stand behind the stumps also. Then the coach will tell you that, okay, no, you have to stand in front of the stumps. Right? But unless you go to the pitch, you're not going to learn. Okay? And usually people don't look behind to see whether you have raised your hand or not. Okay? Most of the people will forget. I mean, there's no real negative thing about raising your hand and being incorrect. In being incorrect just means an opportunity to learn. Being incorrect very likely reflects on the fact that either our education wasn't great, or very likely we will forget these concepts. That's absolutely normal. It's absolutely human. Okay, if we were to, I mean, we have finite storage space, right, in our brains, and whatever is more relevant and newer is going to replace whatever was there originally. Okay, I can guarantee you, no matter how great or terrible this class is, you are not going to remember these concepts 2 years later. I will guarantee you. Okay, but you will learn the skills to know where to find appropriate information, and instead of spending 2 days in order to understand that information, you will probably spend 1 to 2 hours. I'm not trying to achieve a case where you will remember everything 2 years later. Okay, you will learn the skills to do so. Okay, kind of riding a bicycle. Okay, you will not learn the quirks of the bicycle that you are riding today. Maybe the bicycle today that you rode has a little bit twisted handle, so in order to stabilize you might be doing this. 2 years later maybe you got a brand new bicycle. Okay, that exactly how you ride is going to be different. Okay, but you'll still be able to ride it. Okay, and if you are going to learn to ride a motorbike, you will need to learn a little bit. It will take a bit more of time, but if it is, let's say, an auto gear motorbike, you won't take 3 days to learn it. It will probably take maybe a couple of hours, right? And that's what we want to achieve in these courses. I mean, that's my perspective. Of course, you can have a slightly different perspective. Okay, so yeah, it's a normal part of learning process to not remember things, and this are not remembering things about sign convention is quite confusing. So it's perfectly fine that you didn't remember. Okay, so we will represent the stoichiometric coefficient by nu. K is the first one is the species. The next one is for reaction. Okay, so if we were to make the matrix for N2, H2, okay, the nu K for nitrogen is going to be -1, for hydrogen is going to be -3, for NH3 is going to be this and +2, and for AR 0. Okay, by the way, that mistake, I mean, I'm very tempted to say I made that mistake purposely, but that -2 was an honest mistake. I didn't even realize that I was putting -2. And after 20 years of teaching, if I can do that in front of all of you, yeah, you can also make those mistakes. Okay, if you had not corrected me, then that would have stayed on. Okay, the other way to write this reaction is -1 okay, and we can skip this particular part. Okay, and this we can represent as okay, summation from k equal to 1 to ns of nu k ak. That is the standard way of writing any reaction. Okay, so these are the stoichiometric coefficients. Yeah, and if you have multiple reactions, this form a matrix of stoichiometric coefficients. Okay, let's say this, if this were a reversible reaction, but you are writing this as a pair of forward reactions, this will be 1 3 minus 2 0. Okay, you often, people sometimes write it as a reversible reaction, sometimes people write it as first reaction is forward, second reaction is reverse. Okay, you will write it reversible reactions most of the time. You will write it as forward reverse pair if you do not have the thermodynamic information to calculate the coefficients, the equilibrium constant. Okay, again we'll come to that much later, but just mentioning. Okay, so that's the definitions of stoichiometry. Okay, extent of reaction. Very simply, extent of reaction, again we'll have to write down the reaction. Okay, so extent of reaction is how much the reaction has progressed in terms of moles. Okay, so again an example, let's say you have 10 moles of nitrogen, 20 moles of hydrogen. If the extent of reaction is 5 moles, then how much amount of N2, H2, NH3 are left after the completion of reaction where the extent is 5? Yeah. So let me talk about N2. We started with 10 moles. Okay. 5 moles of N2 has reacted. Okay, so by sign convention we'll put a negative sign because 5 moles have disappeared because of reaction, so we end with 5. What about hydrogen? Minus 15. Started with 0. How much formed? Okay, so how did we do this? These values, if you notice, are nothing but extent of jth reaction, zeta j. Okay, if we are only looking at one reaction, this is what this is. Okay, this is what you have implicitly done. I'm just writing the notations explicitly now. That's the only difference. Okay, okay, let us say if there are m number of reactions, reaction 1, reaction 2, reaction 3, reaction 4, and let's say we know the zetas for each of the reaction. All we need to do, we add them up after multiplying by the individual coefficients. and this term will just be replaced by summation that's called as NR as number of reactions. What's the conversion? What's the conversion of nitrogen? %50. What's the conversion of hydrogen?
75%.
75%. How did you calculate conversion?
Start minus n by start.
So conversion this will be if it's a batch type of a reactor. If it's continuous reactor, it will be in minus out by in. Okay, what in and what out? It should be, or what start and what end? It should be number of moles at the start, number of moles at the end, molar flow rate in the inlet, molar flow rate in the outlet. Not mass fractions, not, well, mass fractions, yes, but not mole fractions. Okay, not partial pressures, none of that. It should be molar flow rate in out or moles at the start, moles at the end. Not concentration at the start, concentration at the end, not concentration at the inlet, concentration at the outlet, not mole fractions in the inlet, mole fractions out the outlet. Okay, it will be number of moles at the inlet, outlet, or number of moles at the start or end. Okay, and that's essentially what the next few slides are going to say. So N converted is nothing but the box term, okay, and therefore the number of moles that will be there in the mixture is given by this. Maybe that's what I should have used. Okay, and this is the definition of conversion. Okay, we will use capital X for conversion. Okay, we will use the terminology U for linear velocity, or just velocity. We will use Q for volumetric flow rate. We will use F for molar flow rate. We will use capital X we will use small x for mole fraction. Okay, we'll use capital P for pressure, small pk for partial pressure. Okay, you'll have these slides immediately available. Even at the end of the day today, he'll put the slides. If you have seen the, I'll show that in a bit. Okay, so yeah, so if it's a single reaction, the conversion is just given by this formula. Okay, and if there are multiple reactions, then the conversion will just be given as negative of this term divided by nk naught. Okay, this term that I have circled is not a term that you can measure. Okay, the things that you can measure are things in the moles in the inlet, moles in the outlet, and so on. Sometimes you can measure the mole fractions in the inlet and outlet. If you measure mole fractions in the inlet and outlet, you have to then convert them to molar flow rate. Okay, example over here. Okay, let's say argon is 0. Okay, what's the mole fraction in the beginning of nitrogen? Or nitrogen mole fraction in the beginning? 1 by 3 or 0.33. What's the nitrogen mole fraction at the end? 5 divided by 20, right? 0.25. Okay, remember conversion was 50%. Do you get 0.33 minus 0.25 divided by 0.233? What is it? Is it 50%? Clearly not, right? Why does that happen? Because there is net loss in number of moles because of reaction. That net loss in number of moles, again, just fast forwarding ourselves to 2 weeks or to 1 week from now, that change in number of moles is that epsilon term that you have used in your undergraduate. Remember that epsilon term? Mole expansion coefficient, volumetric expansion coefficient. Okay, I don't use mole expansion coefficient, volumetric expansion coefficient. We'll derive things or go across things from first principles. Okay, but that's the genesis of that term. Okay, and if you're not chemical engineers and you haven't encountered epsilon, or as chemical engineers you don't remember epsilon, perfectly fine. Okay, we will absolutely cover those concepts, but in a slightly different way, a way that is convenient, irrespective of whether we are looking at one reaction or 100 reactions, or one species or 100 species. Okay, and finally, rate of reactions, and this is the IUPAC definition. The rate of reaction is nothing but the conversion of a single reactant with time at constant volume and constant temperature in a closed system. So if we have a constant volume batch reactor, only then is the IUPAC definition valid. Okay, so the IUPAC definition of R is okay, that's not a valid definition for a course like CRE, where we are interested in flow systems and things changing with respect to pressure and temperature and volume and so on. Okay, it's a perfectly valid definition, but the problem with the definition is how you are going to use it. For example, if there is a semi-batch reactor and you use this definition, it's wrong, because you have to account for the moles that are coming in also. Okay, that's something that we will take up in the next lecture. We'll talk about those issues in the next lecture. Okay, but today we are just finish off with a few things. Okay, rate of reaction. Okay, we will call the rate of reaction for this as R. We will not use the terminology minus RA. Okay, how is that related to R? I will come to that very soon. Okay, rate of formation of species, we will use capital R. Okay, capital R is going to be nothing but, if it's a single reaction, this is what it is going to be. And this is what this is going to be. Okay, we will start off the next lecture from here. Okay, we will go over these concepts again in the next lecture. Okay, any questions? Okay, just a 1 minute recap what we have done. We have really started with, you know, revisiting the 3 ideal reactors, which we are going to cover probably a few weeks later. We are going to cover next week as well, but that's more from recapping some of these trends. We took an analogy equivalence between batch and continuous stirred tank reactor, and both as special cases. And we took an analogy between plug flow reactor and batch reactor, and a plug flow reactor and a CSTR. Those analogies are valid only if the volume is not changing because of reactions. Okay, again, that's a little bit of nuance we'll come to later. We have listed the various reactors over here. Thereafter, we defined the stoichiometric coefficients. Thereafter, we defined the extent of reaction, and we can use the extent of reaction in order to calculate the rate of reaction. Okay, rather than the IUPAC definition, the extent of reaction definition is a more robust definition, but the problem with that definition is extent of reaction is a value that one needs to compute from concentrations. It's not a measurable quantity. So again, these IUPAC definitions, remember, it is for a closed system. That means it's for a batch reactor that does not undergo change in volume, does not undergo change in temperature. Only under those conditions the IUPAC definition is a valid definition. Okay, so as far as we are concerned, we are going to look at reaction rate from a molecular perspective, and then use this as a balance equation for a batch reactor. Okay, and if you remember the first or second chapter in Fogler and Levenspiel, that's what they start off with. Okay, the problem with sometimes with the undergraduate text is we start off with an assumption in chapter 1 and 2, and then by the time we come to chapter 10 and 11, we have forgotten all of those assumptions. So instead, we are going to start off with a broad model, and we will each time we will treat a specific case as a specific case of that broad model, so that you will remember the assumptions each time that you are using a new system. Okay, that's the difference that we are going to have with respect to undergraduate. Other than that, everything that you have done in undergraduate is very much valid. Okay.